Welcome back to statistics and probability. This unit's going to cover random variables. We'll explore how probability models real-world situations using random variables. And we'll start by distinguishing discrete and continuous random variables. Then we'll learn how to transform and combine them to analyze more complex scenarios. From there, we'll focus on important models like the binomial and geometric random variables, including how to calculate expected values, means, and standard deviation. So we're going to first start with looking at constructing probability distributions. And some of this first section might be review for you. If it is, I think that's a good thing. So probability distributions ask us to graph the relative frequency of events occurring. In this problem, it says that somebody got a new pet lizard and they're collecting data on that lizard for 10 days, 3 times a day to see if the lizard is awake or asleep. A means it's awake, S means that it's asleep. And we're supposed to drag these bars. I'm just going to draw them, but it's on Khan Academy, you can drag the bars and you can actually plot the graph more precisely that way. But it says drag the bars to make a relative frequency plot that shows the proportion for each possible number of times the lizard is sleeping in a day. And it has all this data here. So this question is asking us to figure out how many times the lizard is sleeping. The first time I did this, I read it very quickly and I found how many it was awake. So just be sure to read the problem carefully when you're doing these. So we're going to count how many times that the lizard is sleeping for each day. So 0 times 0, 1, 2, 1, 2, 1, 1, 0, and 3. So now we have our data and we're going to make a probability distribution with the relative frequency for each of these scenarios. So if it's sleeping 0 times, there's 3 times that it's sleeping 0 times out of 10 times altogether. So you get 0.3 for 0 times. And we can put that on our graph. And if we want to know how many times it does one time, that's 1, 2, 3, 4 times out of 10, or 0.4 for one time. And like I said, this might be a review for you. 2 times, 1, 2, just 2 times, 2 tenths. So 2, 0.2 for 2 times. 3 times is just 1 out of 10 times, or 0.1. And that's all we have to do for this problem. Okay, let's look at one more though. This next one's a little bit more complex, I think. It says Jerry likes to dress sharp. Each day is independent. And that's important for these problems, saying that when we're talking about probability and independence. It's a keyword that you should look for in probability problems. And we'll talk about that in more detail in some later lessons. But for now, it says each day is independent, and he has an 80% chance of wearing a blue shirt and a 20% chance of wearing a red shirt. X is a random variable that represents the number of blue shirts that Jerry wears in the next 2 days. Plot the probability for all possible values of X. So we want to know the probability that he wears 0 blue shirts, 1 blue shirt, and 2 blue shirts over the next 2 days. So we can start by making a table of this. We can say this is day 1 and this is day 2. And we're going to list all the possibilities. So for day 1, he could wear a red shirt. Day 2, he could wear a red shirt. Day 1, he could wear red. Day 2, he could wear blue. Or day 1, he could wear blue. Day 2, he could wear blue. Day one, he could wear blue. Day two, he could wear red. Those are all of the combinations. So when you're doing probability problems like these, it's a good idea to try to write out all the possible combinations, unless there are so many that it becomes just way too difficult to do. But in this case, we're just dealing with two items, so it's not too bad to be able to list out all those combinations. So now the probability for a red is 0.2. And we want to know he's wearing a red shirt day one and a red shirt day two, and means we multiply our probabilities. So now this is 0.04. So he's a 4% chance of wearing a red and red. For red and blue, we have a 0.2 chance or 20% chance that he's going to wear a red shirt, and 80% chance he's going to wear a blue shirt, or 0.16. And these should all add to 1 for what we're getting for our final answers for these. 0.64, and a blue and a red shirt is 0.8 and 0.2, which is also 16%. Okay. Now we want to know 0 blue shirts, 1 blue shirt, and 2 blue shirts. So for 0 blue shirts, that would be, it's going to do this, say 0 blue shirts. That would be if he wore red and red. So that's 4% or 0.04 for 0. So we would put 0.04 on our graph. We would just graph it about there. Yeah, it's a little high, but still it's 0.04 for that one. Now let's look at if we had 1 blue shirt. There's 2 different combinations for that. If we had 1 blue shirt, that's he wears a red shirt the first day, a blue shirt the second day. And it's also if he wore a blue shirt the first day and a red shirt the second day. So we have to add those probabilities together. And that's just 0.16. Oops. 0.16 plus 0.16, which is 0.32. So the probability he wears 1 blue shirt is 0.32. Okay, and then the last one is if he wears 2 blue shirts. And that would just be the last B and the B on our table here, which is 0.64. And we're just going to plot that on the graph. And again, if you're using Khan Academy, you can drag these values up. So you just click and hold the green and then drag up like that. Okay, we're going to look at one more with coins. Anna challenges Sarah to a game where Sarah flips a coin. It's a fair coin. That means that it has an equal possibility of getting heads or tails. And then she randomly chooses a card from a very small, it should say very small deck of cards that includes only 1 jack, 1 queen, 1 king, and 1 ace. So there's only 4 cards in this that she's picking from. So that's what the game involves. She flips a coin and draws a card. The only way Sarah can win is by flipping heads and then choosing either jack or a queen. So we're gonna list our possibilities for this to see the probability of her Sarah winning and Sarah losing. So we have 1 coin. It can be heads or tails. And we have 4 cards. And it can be jack, queen, king, or ace. So those are all of our possibilities for the coin and the cards. Now we're going to list the outcomes. I'm just going to write this here, list possibilities. That way we're labeling what's going on here. Listing the outcomes. So there are many different combinations of what could occur. So she could do heads, jack, heads, queen, heads, king, heads, ace. Or she could do tails, jack, tails, queen, tails, king, tails, ace. So there are 8 possible outcomes. Okay, now we want to identify the winning outcomes. So the winning outcomes is heads, jack, or heads, queen. Those are the only ways that we can win this game that they're playing. So that's 2 winning outcomes. So the probability for a win is 2 out of 8, or 1/4, which is equivalent to 0.25. And so we're just going to put that on our graph. And we only have win or lose, so it's got to be for the probability of losing. And the complement of that, so 1 minus the probability that they win. So that's going to be 1 minus 0.25, which is 0.75. Okay, so again, we have to list out all of our outcomes for these, and it just kind of depends on what the problem is telling us. So just think carefully about what the possibilities are and the outcomes for these. All right, probability models. This next section's a little bit easier. Most of these, I think actually maybe all of these questions are, we have to find a probability that adds to 1. So we have the probabilities of these 3 different employees here, and we're asked to find what is the probability that James will open the store on a given day. So it says that this is the probability that these 3 people will open the store. And we want to find the probability that James does. So if there's only these 3 people working, all of the probabilities should add to 1.0, or 100%. So Chelsea is 0.3. Ivy is 0.1, and then plus something is going to equal 1.0. Well, we can just say 1.0 minus 0.3 minus 0.1, 1.0 minus 0.4, which is 0.6. So that's all we have to do for this problem. Just knowing that all of our probabilities add to 1. Let's look at another example. And these should all be review for this next section, but so it's not too bad here. It says Dahlia owns a gravel pit. She took a random sample of rocks and counted 58 sedimentary rocks, 213 metamorphic rocks, and 522 igneous rocks. Use the observed frequencies to create a probability model for Dahlia, randomly selecting 1 rock from her gravel pit. Input your answers as fractions or decimals rounded to the nearest hundredth. So we have the types of rocks, 3 types of rocks, and we want to find the probability. Now, the first thing that we should do is calculate the total. Once we know the total, then we can figure out as a fraction what each of these rocks are in terms of their probability. So the total would be 58 plus 213 plus 522, which equals 793 for our total. So now for each of these, it's going to be a fraction out of 793. So sedimentary rocks is 58, metamorphic 213, igneous 522. And you might be able to just leave the problem like that. But if we wanted to change this to a decimal to the nearest hundredth, let's do that just to demonstrate that we can round these decimals. We want to the nearest hundredths, so I got 0.073, but we would round that down to 0.07 for the first one. 213 divided by 793 is 0.2. I got 0.268, but we'd round that up to 0.27. And then the last one looks like that would give us 0.658 or 0.66. So these should add up to 1.0, but if you end up rounding them, sometimes they don't. Sometimes they just add up to 0.99. But that's essentially what we need to do for these problems. All right, one more of these. There are these three people, they're racing each other. There's no other racers. Only one person wins. There's no ties allowed. And they're telling us all that information here to demonstrate that all of the probabilities are going to add up to 1.0. This shows an incomplete probability model for who's going to win, and we want to find the probability that Rachel will win a race. So Manny has a 0.35 probability. Peg has a 0.25 probability of winning, and that puts us at 0.60. So for Rachel, let me write it in probability notation. The probability that Rachel wins we use the complement rule is 1 minus 0.60, which is equal to 0.40. And the probability rule of that all probabilities must add up to 100, it's also written like this. The sum of probability of x is equal to 1.0. That's a sigma notation for sum. So the probability that Rachel wins is 0.4. All right. Look at some other ones next with discrete random variables. So here we have a probability table, and we have some missing data in this table. We're also going to use the complement rule for these. All of these probabilities have to add to 1.0, but notice that this last category says 5 or more. This is still a category of just one value for what h is, even though it says 5 or more. This still includes everything greater than 5 and 5. There also can't be negative values for this specific problem. It looks like it's about the U.S. Census Bureau trying to obtain information about households in the U.S., which is how many people reside in each household. So there can't be a negative value of people in a household. But the very lowest would be 0, I suppose. But this is based on data from 2014, and it's a partially completed table. And so again, we would add all of these probabilities together. If we add all of those in the calculator, we get 0.88. And then we would use the complement rule. So the probability that h is equal to 0 is 1 minus all of the data in the table that they gave us, which is 0.12. And that's all we have to do for finding the missing probability in the table. Same basic idea as the graph ones. Okay, this one's a little bit different, but it's kind of the same. Cora's playing a game that involves flipping 3 coins at one time. Let the random variable h be the number of coins that land showing heads. here's the probability distribution for H. So we have number of heads, 0, 1, 2, or 3. And we have a probability for each of these outcomes already given here. So it says, what's the probability that she flips more than 2 heads? Well, more than 2 heads is just if she flips 3 heads. And it tells us clearly on the table is 0.125 for that one. So like I said, these aren't too bad. We're going to do one more question. It's a little bit tougher. And then we're going to jump to expected value. So this is based on a real world phenomenon called Benford's law, which tells us that the first digits of data entries in most real world data sets are not uniformly distributed. And the most common first digit that shows up on any data set is 1, followed by 2, and so on, with 9 being the least common digit that shows up first on a list of numbers. And this is again called Benford's law. So we have a probability distribution for the probability of these numbers appearing first. So you can see 1 is the most probable at about 0.3 or 30% probability that a 1 shows up first in a list of numbers. Okay, it says find the indicated probability. The probability that D is greater than or equal to 2. That says the probability that a digit is greater than or equal to 2. So that tells us we want to add up all of these probabilities, because greater than or equal to 2 means 2, 3, 4, 5, and all the way through 9. So you can add all of those up, or again, you can use the complement rule. You can say that the probability that D is greater than or equal to 2 is equal to 100% or 1.0 minus the probability that D is less than 2. Not less than or equal to 2, because we're not including that it equals 2, only that it's less than 2. If that's a little bit confusing for you, you can still just add these up and not do the complement rule if that's easier for you. But if this makes sense, this is just a shortcut method that you can use. So we get 0.699 for that. And that's our final answer. All right, next we're going to get into a topic called expected value. And the expected value is the average value of a random variable after multiple trials. So you can calculate it by multiplying each possible value by its probability, which is how often something occurs, and then adding those results. Because probabilities add to 1, this automatically gives us a weighted average, even if the result isn't a value that you'll actually see in a single trial. So the weighted average, again, is just an average that it could show up in real life or maybe not. And I think this first example is, well, I think it's a good example of how the answer that we get isn't really a value that we'll typically see, but it's just how much that we would expect to either get or lose in terms of money on average over a long period of time, with, in this case, buying an insurance policy for a house, an optional insurance policy. It says Marciel's considering buying flood insurance that costs $600 and it's worth $50,000 if her home floods. Based on previous years, she estimates that there's a 2% chance of her home flooding this year. Find the expected value of buying the flood insurance policy. Okay, so it might be tempting to think to yourself, well, she's spending $50,000. There's a 2% chance. Let's just multiply 50,000 times 2%. If you're thinking that, you're very close. But we have to also include the fact that this insurance policy costs $600. So the benefit is actually $50,000 minus the 600 that we spend. So if the house ends up flooding, we don't make $50,000 on the insurance policy. We only would make $49,000, $49,400. So it says find the expected value. The notation for expected value is EX for expected value. And if we want to find EX of it flooding, we put yes, floods, then that would be $49,000, $49,400 times the 2% chance that it does flood. So we have an expected positive value that we would get back of $988. The expected value of if it doesn't flood is, well, if it doesn't flood, we wasted or we spent $600. I shouldn't say wasted because it's still insurance. So we spend $600 and there's a 98% chance that we don't need it. So we're going to multiply by 0.98, and this gives us a negative expected value of $588. Now, to find the total expected value of this policy, given the probabilities, we would add these together. And we're just focusing on adding those together. 988 minus 588. And that gives us an expected value for our total expected value of $400. So the expected value for the flood insurance policy is a positive amount. So that means that we would expect to gain money if we repeated this multiple trials in a row, given that there's a 2% chance of the home flooding. And that seems like a very low percent chance. But according to the statistical reasoning of expected value, we would expect to make a gain. Now, we also use expected value in gambling type problems to figure out how much money that we would make, maybe like at a casino or something like that. And this next problem is going to show us not quite in that depth yet, but we are going to look at a discrete random variable and seeing the probability of something occurring. And I'm going to use this next example to say, we're going to just say that we're rolling a, a five-sided die. So most of the time when you roll a dice or one die, there's six sides, but we're going to pretend like we have a five-sided die, like an irregular looking die that we're rolling. And that die gives us the probabilities of it landing on each number. So sometimes I'm trying to think of there's some board games that have some very interesting looking dice that aren't normal dice, and some of the sides of them aren't even the same size. So I think that would be a good example for this table data here. So the probability of getting a 1 is 9%, getting a 2 is 3%, getting a 3 would be 52%, and so on. And so it wants to know what's the expected value of X. If we rolled this die over and over and over again, and we know the probabilities of each of these numbers, what number would we typically tend to get each time? So the expected value, again, is the average value of the outcomes over many trials. So we're going to write our expected value notation like this. And it's the sum of x times the probability of whatever the value is. In this case, we're saying uppercase X equals X. So the sum of each of the occurrences times the probability of each occurrence. We're adding those together. That's what this sigma notation means. So for a 1, the probability of getting a 1 is 0.09. And then we just keep adding these together. 2, 0.03. For a 3 is 0.52. I'm going to just make a new line because we're out of room there. 4 and is 0.24 plus 5 times 0.12. Okay, so when we do 1 times 0.09, we get 0.09 plus 0.06 plus 1.56 plus 0.96 plus 0.6. Okay. Now, if we add all these together, we should get a number that we don't actually get on the die, and that's okay. But I'm just adding these together, making sure. Got 3.27. So that's our expected value for X. So if we roll this, we would expect to get, I would say, a 3 or a 4. If we did this over and over and over and over and over again. And we can see that very, very clearly here that we have over a 50% chance of getting a 3. So that definitely falls in line with our given probability in our table. But that's how you calculate the expected value for this. Let's look at one more expected value with a graph. It's the same basic idea though. We don't even know what X is. We just know the probability for X, and we're given the values of X, but we don't know what X is defined as. We're just saying that it's X. So we want to know the overall expected value of X. So we're going to do the same thing for this one, except now we don't have table data. We've got to look carefully at the graph. So when X is 0, there's a 0.2 or 20% chance that we get a 0. When it's 50, there is a 15% chance that it's 50. And we'll zoom out here so we can just do the rest of these. Maybe 100 times 0.45 plus 150 times 0.2. Okay, so 0 times 0.2 is just 0 plus 50 times 0.15 is 7.5. 100 times 0.45 is 45. And 150 times 0.2 is equal to 30. And then we just add all those together, and we would say we would expect X to be 82.5. So that's what we get for our final answer for that one. All right. So this next section is the mean of a discrete random variable, which is basically just the expected value again. When we write the mean of something, let me write like this. So the expected value is equal to the mean of X. And mu is this U, and that just means average. So it's or average or mean. So there's two different ways to write expected value, basically. So we'll go through these a little bit quicker. This person catches a fish. There's a 70% chance that it's a northern pike and a 30% chance it's a walleye. Let W be the random variable that represents the number of walleye that Eva gets if she catches 2 fish. Okay, so I think there's a bit of extraneous information in this. We're just going to look at the table again and calculate the mean of W. And so again, that's the same thing as expected value, but I just want you to know the notation for this. So 0 times 0.49 plus 1 times 0.42 plus 2 times 0.09. So we've got 0 plus 0.42 plus 0.18. Looks like we should get 0.6 for our final answer. Okay. All right. That was, I think, basically the same thing that we just did. So I only put one example here for that. Just again, know that the expected value notation can be interchangeable. All right. Standard deviation of a discrete random variable. This is the last section for this part of discrete random variables. So this has to do with the expected value of how much that this person is going to win at a carnival game. Carnival games cost money, but sometimes you can win money back at a carnival game, not just prizes, but you can actually win money as a prize. So that's what this problem is about. Now, this problem already gives us the expected value of the game. So let's read through the problem first before we go a little even too far here. So the game costs $5 to play. The player gets to take 2 shots for basketball shots. If they miss both shots, they don't get anything. If they make 1 shot, they get their $5 back. If they make both shots, they get $10 back. And it says Talia has a 40% chance of making this type of shot. Here's the probability distribution of X, the amount of money that Talia gains from playing the game. Okay, so they calculated for us that the expected value is she's going to lose $1. Now, that's that's I guess maybe not the most accurate way that we would want to explain our wins or our losses, because expected value tells you the average gain or loss. But this question's asking us to find the standard deviation, which is how much those results are going to vary from that average. So the standard deviation, in order to calculate the standard deviation, we have to know what the expected value is, which we do know. And we also have to know the probabilities of each instance for X. So in order to calculate the standard deviation, we're going to use the variance. Because when we square all the values with variance, we end up getting all positive values that we're working with. So just as a quick review for notation, standard deviation of X is written like this. The variance of X is written as the standard deviation of X. Excuse me, the standard deviation squared of X is the variance of X. So we're going to use the variance to solve this problem. And the formula for variance in terms of probability is that the variance of X is equal to the sum of X minus the expected value squared times the probability of X. And it's the sum of, so we're going to repeat this formula and add each of the parts for all three of these sections in our table. So let's start by doing that. So um, actually, let me expand this formula first before we start plugging stuff in. So if we expand this sigma formula for variance, this becomes x1, our first data point, minus the expected value of x squared times the probability of our first thing happening. I'm just going to write it as P1 like that. And then we're going to repeat the process for each of our probabilities for each of these instances occurring. And we only have three instances occurring, which is a good thing. That's a little bit less that we have to write out there. But now let's plug all these values in and we're going to see what we get. So this is going to be, and maybe I shouldn't have written P1, P2, and P3. Let me write that as the probability that we lose $5. So the probability of a -5. The probability that we get $0 from playing the game, and the probability that we get $5 earned from playing the game. All right, so now this is going to be for x1 is going to be -5. That's where our x value is, minus the expected value is -1. Minus -1 is going to be +1, but we're just going to leave that like that and then square it times the probability that we have -$5 is 0.36. Okay, then we're going to move on to the second data point and do the same thing. 0 minus -1, square that, times 0.48, plus the third data point, 5 minus -1, square that, times 0.16. Oops. Let's go scroll back up here, right to the edge of the page there. Okay, so now let's calculate all these values and just be careful with the double negative. So we have -5 plus 1 gives us -4 squared. And I'm just going to write the probabilities here again. And it's just going to be 1 squared times 0.48 plus 6 squared times 0.16. Now, it's nice that they give us these probability values in this problem. It's not always going to be the case in a real world situation, but we have the data to calculate this in this case. All right, so let's keep going. Remember, when you square a negative, you get a positive, so 16 times 0.36 plus 1 times 0.48 plus 36 times 0.16. Okay, and then we should get 5.76 plus 0.48 plus 5.76. We'll add all of those together. And it looks like we get 5.76, 0.48. We get exactly 12. Now, this is the variance. The variance is the standard deviation squared. So this 12 is that. Maybe I should write of x. So that's what that 12 represents. We want to find the standard deviation. We want to find this. And so all we have to do that is just take the square root of both sides. So now we got the standard deviation is about equal to, I'm going to put about equal to 3.464. And it wants us to go to 2 decimal places. So this is going to be $3.46. Now let's talk about what this even means. So remember, expected value tells us the average gain or loss, and standard deviation tells us how much the results vary from that average. So this means that most of our results are going to be around -$1 for our expected value, plus or minus, we'll say, one standard deviation, which is about 60, I think 68% is one standard deviation from the mean in a normal distribution. So one standard deviation is 3.46. So we can expect our results to be about -$4.46 or $2.46 each game. So that should be our range of values that we would expect to get in this game. Okay. All right. Let's look at one more of these. And we're going to do the same basic calculations for variance and standard deviation. This person is sick with an infection, and the treatment involves taking a $20 drug, and it has a 90% chance of curing the infection. If the drug doesn't work, the patient takes an $80 drug that's almost guaranteed to cure the infection. The table below displays the probability distribution of X, which is the total amount of money that a randomly selected patient spends on the treatment plan. And they already calculated the expected value for us of $28, and we want to find the standard deviation of X. So again, we're going to calculate the variance for this. So our expected value is 28. And so we know that to find the standard deviation, we're just going to find the variance of X first. And that's equal to the sum of our X values minus our expected value squared times the probability of X. And here we only have two different outcomes that can occur. So if we rewrite this, this becomes our first scenario minus the expected value squared times the probability of the first thing happening plus our second instance of what's occurring minus the expected value squared times the probability of the second thing happening. Okay, we're just going to plug in these numbers now. So we have 20 minus 28, square that, times the probability of 20 is 0.90. Okay, and now our second scenario is it could be $100 minus the 28 squared times our probability that's $100 is 0.10. So we're doing the same thing as example one, except we only have two different items to add together here. So now this is -8 squared times 0.90 plus 100 minus 28 is 72 squared times 0.10. And we should get a fairly large number for that 72 squared. This becomes positive 64 times 0.90 plus 5,184 for 72 squared times 0.10. Okay, when we multiply those, The variance of x should be 57.6 plus 518.14. And that gives us 518.4 plus 57.6, 576. And then the very last thing, we want to find the standard deviation. So we're going to square root both sides. And so if we take the square root of that, we get exactly 24 for our standard deviation. Okay, so most of the outcomes are going to be the expected value plus or minus one standard deviation. You can think of it like that when we're talking about a normal distribution. So we have a normal distribution. Here's the mean in the middle, and then we have here's minus one standard deviation, and here's plus one standard deviation. So most of our data should fall within here. And so when I'm doing this calculation like earlier when we had our $3.46, let's do that again for this one to figure out what the standard deviation would be. So we have $28 was our expected value, and we're going to say plus or minus one standard deviation. So 28 plus or minus a standard deviation is 24. And so we're going to figure out what those two values are. That's 28 minus 24, which is $4, and 28 plus 24, which is $52. And so we can expect the range to be about between $4 and $52. All right, so that is everything on part one of random variables, covering discrete random variables.